Okay, before we move further into it, let's make one point clear. What do we mean by when I say electric dipole? Now, electric dipole happens to be a system of two equal and opposite charges separated by very small distance. So, if I've got two equal and opposite charges, let's say one charge of minus q magnitude, another charge of plus q magnitude, and they are separated by a very small distance. Now, this distance is generally considered to be 2L. Now remember, 2L is the entire distance. Now every dipole is defined by a term called as dipole moment. Now dipole moment is denoted by symbol P and is a vector quantity. So being a vector quantity, it will have a sense of direction. What is the sense of direction associated with a dipole moment? It's always directed from the negative charge to the positive charge. So this particular arrow that I am drawing is used to indicate the dipole moment and its sense of direction. Now dipole moment P is equals to Q into 2L. 2L is the length of dipole axis. Length of dipole axis, that is the distance between two charges constituting the dipole, and Q happens to be the magnitude of the charge. Now it is not necessary negative or positive, any charge will do it. Now for a dipole, this is minus q, this is plus q. The distance between them is going to be called as dipole axis. Now a line happens to pass parallel to the dipole axis is called as axial line. So this green line is going to be referred by us as axial line, and a line which divides the dipole axis into two equal halves. So this line is going to be called as equatorial line. So this is the equatorial line and the green one is axial line. Any point that happens to be situated on axial line of a dipole is called as end-on position or simply axial position. Similarly, any point that happens to lie on equatorial line is going to be called as broad side on position or equatorial position. You will be asked to derive electric field at axial position or broadside on position. The number of questions can be framed for derivations, but presently we are not interested in going to the derivation part of it. I will directly go ahead with the result of these. So the electric field at equatorial position is equal to P, which happens to be the dipole moment, upon 4 pi epsilon naught r square minus r square plus L square whole 3 by 2. Now this formula is for electric field due to a long dipole. For a short dipole, the electric field will be, and in numerical problem mostly you will be dealing with a short dipole. So electric field at equatorial line for a short dipole will be P upon 4 pi epsilon naught r cube. Now remember, the direction of the electric field at equatorial position is always directed opposite to the dipole moment. So here the dipole moment is directed from left to right and the electric field is going to be directed opposite to it. So in vector notation, this electric field can be written as minus times of P upon 4 pi epsilon naught r cube. So remember this, electric field SI unit happens to be Newton per Coulomb. Now for electric field at any point on axis of a dipole, so E axial will be equal to 2P upon 4 pi epsilon naught r square minus L square ka whole square, 2PR. So E at axial position will be 2PR upon 4 pi epsilon naught r square minus L square. Take care about this. Now for a short dipole, So for a short dipole, R being very less than L, this result will be E axial will be equals to 2p upon 4 pi epsilon naught R cube. 2p upon 4 pi epsilon naught R cube, and in vector notation E axial will be 2p upon 4 pi epsilon naught R cube. Now at axial line, the electric field happens to be parallel to the dipole moment. So remember, this is an important aspect. You should take care about this fact. The electric field at axial line happens to be parallel to the dipole moment, but electric field at equatorial position happens to be opposite to that of dipole moment. Now this fact should be borne in your mind, should be kept into your mind. Now for a short dipole, the axial position's magnitude and equatorial position's magnitude bears a ratio. You can see very easily that electric field at axial position happens to be twice the electric field of equatorial position. So wherever in numerical problem it is a short dipole, and in most of the cases you will be given with a short dipole. Remember, this can be an easy way to get the magnetic field if you know the to get the electric field if you know the electric field at any one of the position. If it is at equatorial position, you know, then you also know at the axial position it will be just the twice of this value. Thank you.